A photograph taken in 1979 showed something scientists were never supposed to see: a plume rising hundreds of kilometers above the surface of a distant moon. At first, the engineer examining the image thought it was a mistake, a camera artifact, a processing error. It was neither. The plume was a volcanic eruption, and it was coming from a moon that researchers had assumed would be frozen solid. The moon is called Io. More than 400 volcanoes are active across its surface right now, making it the most geologically violent world in the entire solar system. Some eruptions launch material so high that it would tower above the orbit of the International Space Station. Lava temperatures can exceed those found in many terrestrial volcanoes, reaching levels hotter than the surface of some stars. What makes this difficult to explain is where Io lives. It orbits far from the Sun, receiving only a fraction of the sunlight that reaches Earth. By conventional expectations, it should have cooled billions of years ago. Instead, it is constantly erupting, constantly resurfacing, constantly rewriting itself. Impact craters, the geological scars found across nearly every solid world in the solar system, are almost entirely absent here. Fresh volcanic deposits bury the evidence before history has time to accumulate. And the deeper scientists looked, the stranger the picture became. The source of Io's heat is not hidden beneath its surface. It is hidden in its orbit. Jupiter's immense gravity stretches and compresses the moon over and over again, generating extraordinary amounts of heat deep within its interior. Neighboring moons help sustain the process, ensuring the cycle never fully stops. The result is a world that has remained active for billions of years, long before the first animals appeared on Earth, long before the first forests, long before complex life existed at all. What Io reveals is larger than a story about volcanoes. It is evidence that gravity can act as an engine, powering entire worlds from the inside out. The same hidden forces operating around Jupiter today may also be shaping oceans beneath distant moons, influencing planetary evolution, and helping create environments where life can emerge. This channel grows because of people who take a moment to like and subscribe. If you're one of them, thank you. It means we get to keep doing this. The story begins with a small point of light that Galileo first noticed through a telescope more than 4 centuries ago. Before anyone knew its colors, its volcanoes, or its restless surface, Io existed as a moving spark beside Jupiter. Through a small telescope in January of 1610, Galileo Galilei noticed that several points of light changed position from night to night. Those observations became one of the most important discoveries in astronomy. For the first time, moons were confirmed orbiting another world. Io was the innermost of the 4 large moons Galileo recorded. Today, we call those worlds the Galilean moons. Yet for centuries, Io remained little more than a distant dot. Its true nature stayed hidden behind distance, limited instruments, and the immense brightness of Jupiter itself. Even its basic dimensions revealed little. Io measures about 3,643 kilometers across, which is about 2,264 miles. That makes it slightly larger than Earth's moon. Its position is more revealing. Io circles Jupiter at a distance of roughly 422,000 kilometers, which is about 262,000 miles. From that location, it completes a full orbit in only 1.77 Earth days. In less than 42 hours, it races around the largest planet in the solar system and begins the journey again. Everything nearby feels Jupiter's influence. The giant planet contains roughly 318 times the mass of Earth and more than 1,300 times Earth's volume. It dominates the region gravitationally, holding an entire family of moons within its reach. From our perspective, That relationship seemed straightforward for a very long time. Year after year, decade after decade, Io remained unresolved. Astronomers tracked its orbit with increasing precision, but the surface itself offered no clues. No mountains could be seen, no canyons, no signs of activity. Nothing suggested that anything unusual was happening there. 369 years passed this way. As telescopes improved, scientists built a picture based largely on expectation. Worlds far from the sun were assumed to cool with age. Internal heat would gradually fade. Geological activity would slow and eventually stop. The moon offered a familiar example, its cratered face preserving ancient impacts across billions of years. Io seemed destined to fit the same pattern. Most researchers expected a frozen landscape, heavily cratered and geologically inactive, a distant relic from the solar system's youth. The assumption felt reasonable. It matched what was known about many other solid worlds, but nature had already written a different story. Near the end of the 1970s, a handful of scientists began examining an unusual possibility. Their calculations suggested that Io might possess an internal energy source powerful enough to keep the moon active. The idea appeared startling, even improbable. Then, only 3 days after that prediction entered the scientific record, a spacecraft arrived with photographs, and everything changed. Sometimes a scientific idea spends decades waiting for evidence. Researchers propose a possibility, refine it, argue over it, and slowly gather support through years of observation. That is usually how discovery unfolds. This case was different. On the second day of March 1979, three planetary scientists, Stanton Peele, Patrick Casson, and Ray Reynolds, published a paper in the journal Science. Their work focused on a strange source of energy hidden within orbital motion. The mechanism had a name: tidal heating. Tidal heating is the generation of internal warmth through repeated gravitational flexing. The scientists calculated that Io might be experiencing this process on an extraordinary scale. Their numbers pointed toward a startling conclusion. The moon should be volcanically active, perhaps more active than any other solid body in the solar system. It was a bold claim. At that moment, nobody had seen a single volcano there. 3 days later, the first spacecraft to reach Jupiter arrived. Voyager 1 swept through the Jovian system and began transmitting images back toward Earth. Among the many people studying those photographs was navigation engineer Linda Morabito. Her task was routine. She was examining an image of Io to help determine precise spacecraft positioning using background stars. Then something caught her attention. Extending beyond the edge of Io appeared a faint crescent shaped feature. It did not match any known moon. It did not belong where it appeared. The shape seemed detached from the world itself. Her first thought was simple: an imaging problem. Instrument artifacts occasionally appear in spacecraft data. Processing errors can produce misleading features. Morabito checked the image again. Then she checked it once more. The feature remained. It was real. What she was seeing was a volcanic plume rising approximately 280 kilometers above the surface, which is about 174 miles. Nothing like it had ever been observed beyond Earth. The discovery immediately transformed the image. Within hours, the Voyager imaging team began searching through additional photographs. The results became even more remarkable. The spacecraft had captured evidence of 8 separate eruptions active at the same time. 8. On a world widely expected to be frozen and inactive. The timing felt almost impossible. The paper describing tidal heating had been submitted weeks earlier, completely independent of the spacecraft observations. Yet publication occurred only 3 days before the flyby. Theory and observation arrived side by side, confirming one another with astonishing speed. In planetary science, such moments are rare, but the photographs held another surprise. Researchers expected to see impact craters scattered across the surface, preserving billions of years of collisions. Instead, crater after crater failed to appear. Careful examination revealed the same conclusion. The surface looked fresh, almost impossibly fresh. A moon roughly 4,500,000,000 years old showed none of the accumulated scars expected from deep time. The images suggested a landscape being renewed again and again, erasing its own history almost as quickly as it formed. The photograph had revealed volcanoes. It had also revealed a mystery far larger than anyone expected. A volcanic world can be explained if it sits close to a star. We understand that idea instinctively. Heat arrives from outside, warming the surface and influencing everything that follows. Yet, when we look at Io, that explanation quickly falls apart. The moon circles far from the sun at an average distance of about 780 million kilometers, which is about 485 million miles. At that range, sunlight is weak. Only a small fraction of the energy reaching Earth arrives there, less than 4%. That is not enough. Scientists also considered another source. Deep inside Earth, radioactive elements slowly decay and release heat. This process helps drive volcanism and tectonic activity. But calculations showed that radioactive heating alone could not sustain the extraordinary activity seen on Io. The numbers refused to cooperate. Something else was feeding the system. The answer emerged from gravity itself. On Earth, we are familiar with tides. Our moon pulls on the oceans, raising and lowering sea levels around the planet. Water responds visibly to that force, but gravity does not act only on liquids. It acts on rock as well. Io lives in a much harsher environment. Jupiter pulls on the moon with enormous strength, reaching deep into its crust and mantle. Those layers are solid, yet they still deform under stress. The process happens continuously, and it begins with the orbit. If Io followed a perfect circle around Jupiter, the gravitational pull would remain nearly constant, but the orbit is slightly stretched. Astronomers call this an elliptical orbit, meaning the distance changes as the moon travels around the planet. Closer, then farther. Stronger, then weaker. With every circuit, the changing pull flexes the entire moon. The surface rises and falls by as much as 100 meters, which is about 328 feet. Imagine an entire landscape slowly swelling upward and then settling again, repeating the cycle every orbit. Rock bends, very slightly, yet over time, that motion matters. The continual distortion generates friction within the interior. A simple comparison comes from bending a metal wire repeatedly. The wire becomes warmer as mechanical energy converts into heat. Io experiences the same physical principle, operating across an entire world. But Jupiter is only part of the story. Two neighboring moons, Europa and Ganymede, contribute their own gravitational influence. Together, the three worlds occupy a precise orbital relationship. For every orbit completed by Ganymede, Europa completes two. During that same interval, Io completes four. This arrangement is known as the Laplace resonance. A resonance is a repeating gravitational pattern that keeps orbital motions synchronized. In Io's case, it prevents the orbit from relaxing into a perfect circle. The stretching continues, the flexing continues, the heat continues. Without that relationship, the internal engine would have faded long ago. Instead, it remains active after billions of years. The result is astonishing. Io releases roughly 100 trillion watts of heat, about twice the amount generated inside Earth through radioactive decay alone. Beneath every eruption lies the same source: gravity, endlessly squeezing a moon that cannot stop bending. Imagine trying to reconstruct a history book whose pages are replaced faster than they can be written. That is the challenge facing anyone who studies the surface of Io. Across the solar system, impact craters serve as memory. Every collision leaves a mark. Over immense spans of time, those marks accumulate and create a visible record of what a world has experienced. You can see this pattern almost everywhere. Earth's moon preserves ancient impacts stretching back billions of years. Mercury carries cratered terrain from the earliest chapters of solar system history. Mars displays overlapping scars that reveal ages, events, and changing environments. Io breaks the pattern completely. After decades of observation, scientists have found no confirmed impact crater anywhere on its surface. For planetary geologists, that absence is extraordinary. A world cannot avoid collisions forever. Asteroids and comets cross every region of the solar system. The impacts still occur. The evidence simply disappears. Fresh material continuously spreads across the moon. On average, the surface is renewed by roughly 1 to 10 centimeters each year. Over long periods, that steady replacement becomes overwhelming. Layers accumulate. Deposits spread outward. Older landscapes vanish beneath newer ones. Any crater that forms begins a race against geology. Burial usually wins. An impact depression may be filled with eruptive material. It may be covered by volcanic fallout. It may be fractured, distorted, or erased entirely before becoming part of the permanent landscape. The result is remarkable. Io cannot preserve its own past for very long. When we look at many worlds, we are seeing history. When we look at Io, we are seeing the present. Its surface composition adds another layer of strangeness. The landscape is dominated by sulfur and sulfur dioxide frost rather than familiar rocky terrain. Vast regions are coated with compounds constantly altered by volcanic activity and changing temperatures. That chemistry creates the moon's famous colors. Bright yellow regions are associated with longer sulfur molecules. Rich red deposits form from shorter sulfur chains. Fresh silicate lava appears dark, sometimes nearly black. Sulfur dioxide frost contributes broad white patches across the landscape. The effect resembles an artist's palette spread across an entire world. Yet the colors are not decorative. They are evidence of active processes unfolding in real time. One of the clearest demonstrations came from the Galileo spacecraft. When it photographed the same region during the 1990s, scientists expected changes to be subtle. Planetary surfaces usually evolve gradually. Io ignored that expectation. Images taken in 1996 and again in 1999 revealed visible differences across the terrain. New deposits appeared, older features faded, patterns shifted. Only 3 years had passed. On geological timescales, that interval is almost nothing. For you and me, 3 years can feel substantial. For a planet or moon, it is barely a moment. Yet on Io, a moment is enough for the landscape to become something new. Every visible feature belongs to a recent chapter, written by ongoing eruptions and destined, sooner or later, to be covered by the next. Counting volcanoes works reasonably well on Earth. We can identify individual mountains, trace lava fields, and compare one eruption with another. Familiar scales help us understand what we are seeing. Those scales begin to fail on Io. Across its surface, scientists have identified more than 400 volcanic features. No other world known to us displays such a concentration of active geology. The landscape is crowded with eruption sites, thermal hotspots, lava lakes, and volcanic depressions spread across nearly every region. Each feature tells a different story. Some are simple vents releasing material from below. Others resemble broad volcanic shields. Still others belong to a category known as paterae. A patera is a large volcanic depression with a relatively flat floor. The term comes from a Latin word describing a shallow dish. On Io, some of these structures reach astonishing dimensions. The most famous is Loki Patera. Its lava lake spans roughly 202 kilometers across, which is about 126 miles. To appreciate that size, imagine a molten feature large enough to contain the entire state of West Virginia, with room remaining around the edges. Even that comparison struggles. Loki Patera alone releases more thermal energy from its surface than all volcanic activity on Earth combined. One structure on one moon exceeds the output of an entire planet's volcanoes. And Loki is only part of the picture. Researchers generally divide Io's eruptions into two broad categories. The first are called Promethean eruptions, named after the volcano Prometheus. These events tend to be persistent, relatively stable, and capable of continuing for very long periods. The second category is very different. Pallanian eruptions, named after Pillan Patera, are explosive, short-lived, and transformative. They can alter huge regions in remarkably brief intervals. A landscape mapped one year may require extensive revision after a major Pallanian event. The distinction helps scientists organize what they observe. Yet, both categories operate at scales that stretch terrestrial comparisons beyond comfort. Energy release is the clearest example. The largest eruptions observed on Io have no direct counterpart in recorded human history. Even the most powerful volcanic events witnessed on Earth struggle to provide useful context. The numbers diverge too quickly. A striking case occurred during August of 2013. Within roughly 2 weeks, astronomers detected three major eruptions occurring across Io. Together, they formed the most energetic cluster of volcanic events observed during the modern era of monitoring. One eruption stood out immediately. Using the W.M. Keck Observatory in Hawaii, researchers observed infrared emissions so intense that the detectors exceeded their measurement limits. Infrared light is a form of heat, radiation invisible to human eyes but detectable with specialized instruments. The equipment could no longer determine the eruption's true brightness. It only confirmed that the event surpassed the maximum range. Consider the distance involved. Io was roughly 780 million kilometers away, which is about 485 million miles. From that vast separation, a volcanic eruption overwhelmed instruments designed specifically to measure astronomical heat sources. At that scale, ordinary comparisons begin to disappear. Longevity is rarely the first thing we associate with volcanoes. On Earth, eruptions begin and end. A mountain may awaken dramatically, reshape its surroundings, and then return to dormancy for centuries. Prometheus follows a different rhythm. Since the Voyager 1 spacecraft first observed it in 1979, every subsequent observation has found the volcano active. Decade after decade, mission after mission, telescope after telescope, the eruption continued. The record remains unbroken. More than 45 years have passed under direct observation. Human beings have watched entire careers unfold during that interval. Spacecraft have been launched, completed their missions, and fallen. Through all of it, Prometheus kept erupting, and it may have been doing so for far longer. Long before the first telescope turned toward Jupiter, the same process may already have been underway, sustained by the deep gravitational engine operating beneath the crust. The plume itself is impressive. Material rises roughly 100 kilometers above the surface, which is about 62 miles. Against the darkness of space, the plume appears bright and pale, composed largely of sulfur dioxide gas. Most major eruptions on Earth rely heavily on water vapor. Prometheus is driven by a very different chemistry. But height is only part of the story. Scientists eventually noticed something unexpected. Comparing observations separated by many years revealed that the plume's location had changed. Between the Voyager era and observations made by the Galileo spacecraft during the 1990s, the visible source shifted roughly 80 kilometers westward, which is about 50 miles. Volcanoes are not supposed to do that. At first glance, the movement seemed puzzling. A volcanic vent is generally tied to a specific location within the crust. If the eruption remained active, why was the plume appearing somewhere else? The answer revealed an important detail about how Io's surface functions. Prometheus is not defined by a single, fixed opening. Instead, extensive lava flows spread outward across the landscape. These advancing sheets of hot material gradually encounter regions coated in sulfur dioxide frost. When that contact occurs, the frost rapidly converts into gas. Scientists call this process vaporization, the transformation of a substance into gas through heating. At Prometheus, the conversion can happen fast enough to generate a towering eruption plume above the advancing edge of the flow. The plume follows the lava. As the flow progresses, the visible source migrates with it. What appears to be a wandering eruption is actually the moving front of an ongoing interaction between molten rock and frozen surface deposits. The scale is considerable. Associated lava flows extend for more than 100 kilometers from the central source, which is about 62 miles. Around the region lies a bright ring of sulfur dioxide deposits, left behind by repeated activity and visible from passing spacecraft. This behavior became so distinctive that an entire eruption category took its name from the volcano. Promethean eruptions are persistent, stable, and capable of continuing for astonishing lengths of time. Even on Io, Prometheus stands apart. It has transformed endurance itself into a geological phenomenon. Some geological processes reshape a landscape gradually. Others arrive with such force that maps become outdated almost immediately. Patera belongs firmly in the second category. If Prometheus represents endurance, Pillin represents release. For years, pressure can accumulate beneath the surface, heat gathers, molten material concentrates below the crust. Then, over a comparatively brief interval, an enormous amount of energy escapes. The results are difficult to ignore. During 1997, while the Galileo spacecraft was studying the Jovian system, Patera produced one of the most dramatic volcanic events ever observed beyond Earth. Scientists watching the data arrive realized that they were witnessing a landscape transform in real time. The changes unfolded rapidly. Within only a few months, a single eruption spread dark lava across approximately 5,500 square kilometers, which is about 2,124 square miles. The affected region exceeded the total area of the state of Delaware. One eruption, one episode, an entire section of the moon changed appearance. The temperatures were equally remarkable. Measurements indicated lava hotter than 1,600 degrees Celsius or 2,912 degrees Fahrenheit. Modern terrestrial eruptions rarely approach such extremes. Even the hottest lavas typically observed on Earth reach around 1,200 degrees Celsius or 2,192 degrees Fahrenheit. The difference is substantial. Hundreds of degrees separate the two environments. Those temperatures help explain why Pallanian eruptions can alter terrain so efficiently. Large volumes of intensely hot lava spread across the surface, covering older deposits and creating entirely new geological boundaries. One neighboring volcano offered a vivid example. Nearby Pele had long been recognizable because of its enormous red deposit ring. The feature stretched across hundreds of kilometers and appeared so persistent that it seemed woven into the identity of the region itself. Then Pilin erupted. Dark material spread outward and partially buried portions of Pele's signature. Features that appeared established on human observational timescales were modified within months. The event revealed an important lesson. Nothing on Io remains guaranteed. Researchers believe eruptions of this type originate from large magma reservoirs. Magma is molten rock stored beneath the surface. Over time, pressure builds within these underground chambers. Eventually, the system reaches a threshold where vast amounts of material escape during a relatively short interval. The behavior contrasts sharply with the sustained activity associated with Prometheus. But another mystery emerged years later. During August of 2013, astronomers observed three major eruptions within roughly 2 weeks. Each displayed characteristics associated with powerful Pallanian activity. The timing raised an intriguing possibility. Could one eruption influence another? On Earth, major earthquakes sometimes trigger additional seismic events nearby. Scientists continue investigating whether similar interactions may occur among volcanic systems on Io. The evidence remains incomplete, yet the question persists. Each new event provides another clue. What remains certain is the aftermath. After a major Pallanian eruption, familiar terrain can disappear beneath fresh deposits. Bright regions become dark, surface chemistry changes, boundaries shift. When researchers return to those locations, they often find themselves studying what is effectively a new landscape altogether. At first glance, you might expect the tallest landscapes on the most volcanic moon to be volcanic mountains. That assumption feels natural. On Earth, towering peaks often emerge from eruptions, collisions between continents, or long histories of uplift and erosion. Yet when we arrive at Io's mountains, the story changes completely. Fire is everywhere here. The mountains come from something else. Researchers studying spacecraft imagery gradually realized that many of Io's highest peaks show little resemblance to volcanic constructs. They lack the broad layered shapes normally produced by accumulated lava. Instead, they appear as immense blocks of crust lifted high above the surrounding plains. Their origin is stranger. Io possesses no confirmed system of plate tectonics like Earth's. There are no moving continental plates colliding to raise mountain ranges, yet the moon continuously covers itself with fresh volcanic deposits. Layer upon layer settles across the surface over immense spans of time. The weight keeps growing. Older crust remains trapped below. As new material accumulates, pressure increases throughout the buried layers. The deeper crust becomes compressed from above, squeezed by the enormous mass of volcanic deposits. Eventually, the crust responds mechanically. Weak regions fracture, large blocks break free, and are thrust upward. You can picture it easily. Press down on a soft surface long enough, and parts of it begin to bulge upward along the edges. Io performs a planetary version of that process. The mountains are expressions of crust escaping confinement. That interpretation leads to an unexpected conclusion. Many of these peaks may preserve some of the oldest exposed material anywhere on the moon. While younger terrain becomes buried beneath fresh deposits, uplifted crustal blocks remain visible because they have been pushed above the relentless resurfacing. Some rise to extraordinary heights. The tallest confirmed example, Bosao Montes, reaches roughly 18,500 meters, which is about 11,494 miles. Its elevation exceeds that of Mount Everest by nearly 10,000 meters, which is about 6,214 miles. The scale is astonishing. Gravity helps explain how such heights are possible. Io is smaller than Earth, producing less downward force on surface rocks. Mountains can therefore rise much higher before their own weight causes structural failure. Even so, many eventually lose that struggle. Spacecraft observations reveal enormous collapse scars along mountain flanks. Vast sections have broken apart and slid downslope. Debris fields stretch across surrounding terrain, preserving evidence of catastrophic landslides that reshaped entire regions. Nothing remains static. Volcanoes and mountains also share a close geographical relationship. Scientists frequently find major volcanic depressions near uplifted blocks of crust. The same compressional stresses that force mountains upward can fracture the crust. Those fractures provide pathways through which magma, molten rock beneath the surface, can ascend. The connection forms an unusual cycle. Crustal pressure creates mountains. Fractures allow eruptions. Eruptions add new material. New material increases pressure once again. But the volcanoes themselves are not constructing the peaks. Instead, they help create the conditions that allow the mountains to emerge, collapse, and transform the landscape before fresh deposits eventually begin the process all over again. Some volcanoes reshape landscapes through rivers of lava. Others build mountains or excavate vast depressions. Pele follows a different path. Its greatest influence comes through chemistry, spreading a signature across Io that can be recognized from astonishing distances. You can see it immediately. Against a world already covered in vivid colors, Pele stands apart. The volcanic center occupies Io's trailing hemisphere, the side that faces backward along the moon's journey around Jupiter. Since the flyby of Voyager 1 in 1979, every generation of observations has found evidence that Pele remains active. Its activity is persistent. Its appearance is unforgettable. Eruption plumes from Pele have risen to heights approaching 300 kilometers, which is about 186 miles above the surface. That altitude extends far beyond the height reached by the International Space Station around Earth. Material launched upward does not simply fall back unchanged. The plume becomes part of a larger chemical cycle that transforms the surrounding terrain. The result spreads outward, far outward. Encircling Pele is a dark red deposit roughly 1,200 kilometers across, which is about 746 miles. It ranks among the largest and most recognizable surface features anywhere on Io. Spacecraft images reveal the ring with remarkable clarity, making it one of the easiest volcanic signatures to identify from orbit. The color itself carries a story. Scientists traced the red material to unusual forms of sulfur known as short-chain sulfur allotropes. An allotrope is a different structural arrangement of the same chemical element. In this case, Sulfur atoms link together in specific configurations that create distinct physical properties and colors. These particular forms are unusual. On Earth, they rarely survive. At typical terrestrial temperatures, the compounds break apart or transform into more stable arrangements. Io offers a very different environment. Surface conditions allow these fragile sulfur structures to persist long enough to accumulate across enormous regions. Understanding them proved difficult. Early observations revealed spectral signatures, patterns of reflected light that act like chemical fingerprints, yet researchers could not immediately identify the source. Laboratory teams eventually recreated conditions similar to those found on Io. Only then did the mystery begin to resolve, linking the strange red deposits to sulfur compounds rarely encountered elsewhere. But Pele differs from many of Io's other major volcanoes in another important way. Its eruptions emphasize gas far more than extensive surface lava flows. Tremendous energy drives towering eruption columns, carrying sulfur-rich material high above the moon before it settles across the landscape. Chemistry becomes the product. The surface records it. Because Pele's deposits are so distinctive, planetary scientists use them as a natural timeline. When another eruption covers part of the red ring, the overlap reveals which event occurred later. When Pele's materials settle on top of neighboring terrain, they establish a different sequence. Layer by layer, relationships emerge. This technique proved especially valuable after the dramatic eruption at Pilin Patera during 1997. Dark volcanic deposits spread across part of Pele's famous ring, creating one of the clearest examples of one volcanic system overriding another on Io. Through that contrast, Pele has become more than a volcano. It serves as Io's identifying mark, a chemical signature visible across a restless world, announcing that powerful geological activity continues on a distant moon, circling far beyond Earth. Patterns are uncommon on worlds driven by eruption. We tend to imagine volcanic landscapes as unpredictable places where change arrives without warning. Yet on Io, one volcanic feature follows a rhythm so regular that astronomers have learned to anticipate its behavior years in advance. Its name is Loki Patera. Among all volcanic structures known beyond Earth, few have been studied as intensely. The feature spans roughly 202 kilometers across, which is about 126 miles. At that scale, the lava lake is large enough to encompass the entire state of West Virginia, with room remaining around the edges. The dimensions alone are remarkable. The heat is even more so. Loki Patera releases more thermal energy than the combined volcanic output of Earth. One structure, one location, a single volcanic system radiating extraordinary amounts of heat into space. But size is not what made it famous. The real fascination began when astronomers noticed that Loki brightened and dimmed according to a repeating cycle. The pattern appeared in infrared observations, a form of light associated with heat that allows researchers to measure temperatures across distant worlds. Something was changing, and it kept repeating. The explanation emerged gradually. A cooler crust forms on top of the molten lake, floating like a dark shell above hotter lava below. Over time, that crust thickens and becomes denser. Eventually, it can no longer remain supported. It sinks. Scientists call this process foundering, meaning the collapse of the cooled surface back into the molten material beneath it. The event does not occur everywhere at once. Instead, the collapse begins along one portion of the lake and advances across the surface like a moving wave. As old crust descends, fresh lava rises to replace it. Newly exposed molten rock shines intensely in infrared light, creating a bright region that migrates around the lake. From far away, the effect becomes visible: a moving thermal signal, a wave of brightness. Observations indicate that this overturning wave completes a full circuit roughly every 400 to 600 days, averaging about 540 days. That regularity makes Loki Patera one of the few extraterrestrial geological systems whose future behavior can often be forecast before it occurs. Researchers, such as planetary scientist Rosalie Lopes, helped develop this interpretation using data gathered from the W.M. Keck Observatory in Hawaii. From a distance of roughly 780 million kilometers, which is about 485 million miles, scientists reconstructed the behavior of a lava lake through changes in its thermal glow alone. The achievement is extraordinary. No spacecraft was required. The lake itself also responds to the same gravitational forces shaping the rest of Io. With each orbit around Jupiter, the surface subtly rises and falls. The entire structure participates in the tidal flexing that powers the moon's volcanic engine. During periods between overturning events, infrared observations reveal a darker appearance as the solidified crust acts like a lid. Then the cycle begins again. Fresh lava emerges, brightness increases, the wave advances. Loki Patera behaves less like a typical volcano and more like a giant clock embedded in the surface of Io, marking time through heat, motion, and the steady rhythm of a world that never truly rests. Everything we have examined so far exists at the surface. Lava flows spread across plains. Plumes rise above the horizon. Mountains fracture and collapse. Yet all of those visible events originate much deeper, hidden beneath layers of crust that no spacecraft has ever directly penetrated. The real engine lies below. And the deeper scientists looked, the stranger the picture became. For decades after the Voyager missions, researchers debated a fundamental question. Was Io hiding a global magma ocean beneath its surface, a continuous layer of molten rock encircling the entire moon? Or was its interior organized in a more complicated way? The distinction mattered. A global magma ocean would imply an interior dominated by liquid rock on a planetary scale. A partially molten interior would suggest a more complex structure where solid and molten materials coexist. Evidence arrived indirectly. The Galileo spacecraft carried a magnetometer, an instrument designed to measure magnetic fields. During repeated flybys, scientists discovered that Io behaved in an unusual way. The moon did not appear to generate its own magnetic field, yet it responded to Jupiter's powerful rotating magnetic field as though something conductive existed beneath the surface. That response became a clue. Molten rock conducts electricity far more effectively than solid rock. By analyzing how Io reacted to the changing magnetic environment around Jupiter, researchers could estimate what might exist below the crust. The results pointed toward a partially molten layer. Current models suggest that beneath the surface lies an asthenosphere, a region of weakened rock containing significant amounts of melt. Estimates indicate roughly 20 to 30% of this layer may exist in liquid form. Beneath that sits a largely solid silicate mantle, composed of rock rich in silicon and oxygen. Deeper still lies a dense core made primarily of iron, or a mixture of iron and sulfur. The core itself is substantial. Its radius is estimated at roughly 900 kilometers, which is about 559 miles. But the debate never fully disappeared. Some measurements remained consistent with the possibility of a global magma ocean. Others favor the partially molten model. The available data places strong limits on what can exist inside Io, yet it has not delivered a final answer. Even after decades of study, one of the moon's most fundamental properties remains unresolved. Another clue comes from the eruptions themselves. Temperature measurements indicate that some of Io's lavas resemble ancient volcanic rocks known as komatiites. These rocks formed on Earth during the Archean era, more than 2,500,000,000 years ago, when our planet's interior was significantly hotter than it is today. Modern Earth no longer produces them. Its mantle has cooled too much. Io appears different. The moon continues generating eruptions that resemble a style of volcanism largely absent from the modern Earth. In effect, Io preserves geological conditions that our own world left behind billions of years ago. That realization gives the interior special significance. When scientists study Io, they are not only investigating a distant moon orbiting Jupiter, they are also examining a living example of processes that helped construct Earth's earliest crust, preserving a chapter of planetary history that has largely vanished from the world beneath our feet. Stand on Io in your imagination for a moment, and one fact becomes unavoidable. Almost nothing separates you from space. The moon does possess an atmosphere, technically, but the word carries expectations that Io cannot satisfy. Its atmospheric pressure is roughly 1 billion times lower than Earth's at sea level. The gas layer is so thin that the surface exists in conditions far closer to vacuum than to any environment we would normally describe as atmospheric. Rocks, lava fields, sulfur deposits, and volcanic plains all sit exposed beneath a sky that barely exists. Yet that fragile envelope is surprisingly dynamic. Most of it consists of sulfur dioxide gas. Two sources continually replenish it. Active volcanoes release sulfur dioxide directly from their vents, while frozen sulfur dioxide, resting on the surface, responds to sunlight. As illumination returns, the frost undergoes sublimation, a process in which a solid changes directly into gas without becoming liquid first. The atmosphere is therefore tied to sunlight itself. As the surface warms, gas accumulates. As the surface cools, gas vanishes. That dependence creates one of the strangest atmospheric cycles known anywhere in the solar system. During each orbit, Io eventually passes through Jupiter's immense shadow. The sunlight disappears. Surface temperatures fall. Sulfur dioxide gas begins freezing back onto the ground. The atmosphere partially collapses. Hours later, sunlight returns. Frost warms once again. Gas rises from the surface, rebuilding the atmosphere that had largely disappeared during the eclipse. Then the cycle repeats. Again and again. Io completes an orbit in less than 2 Earth days, so this transformation occurs with remarkable frequency. Unlike Mars, where atmospheric changes are linked primarily to seasons, Io experiences atmospheric collapse as a regular consequence of orbital geometry. The process is woven directly into the moon's motion around Jupiter. Would the sky appear different to you during these transitions? Only slightly. The atmosphere remains extraordinarily thin even during its fullest state. Yet instruments can detect the change, revealing a world whose gaseous envelope expands and contracts with every passage through shadow. But the atmosphere receives little protection. Jupiter surrounds Io with intense radiation belts packed with energetic, charged particles. Those particles continually strike the surface, breaking apart molecules and driving chemical reactions that scientists are still working to understand fully. Sulfur compounds change form. Surface deposits evolve. Fresh materials become altered almost as soon as they appear. The bombardment never truly stops. At the same time, material is steadily removed from Io. Roughly 1 ton escapes every second. Sulfur atoms, oxygen atoms, and other particles are pulled away by radiation and by interactions with Jupiter's magnetic environment. Over time, that loss becomes enormous. Yet the escaping material does not disperse harmlessly into emptiness. Jupiter's magnetic field captures much of it, guiding the particles into vast structures that extend far beyond the moon itself. What began as volcanic gas and surface frost becomes part of a much larger system, connecting Io directly to the giant planet it circles. Even here, in a place where the atmosphere can fade almost overnight, nothing remains isolated for long. Far beyond the volcanoes, beyond the mountains, and beyond the fragile atmosphere, Io leaves fingerprints across a region of space so large that the moon itself almost seems secondary. Material is constantly escaping. Each second, roughly 1,000 kilograms of sulfur, oxygen, sodium, and related elements are removed from Io and carried outward. Some originates from volcanic eruptions. Some comes from the atmosphere. Radiation and charged particles strip these atoms away and inject them into the surrounding space environment. The journey does not end there. Jupiter possesses the most powerful planetary magnetic field in the solar system. Once these particles become ionized, meaning electrically charged through the loss of electrons, they fall under the control of that magnetic field. Escape becomes difficult. The particles become trapped. Over time, they accumulate. The result is an immense structure known as the Io plasma torus. A torus is simply a ring-shaped object resembling a giant donut. This one surrounds Jupiter at approximately the same distance as Io's orbit, forming a vast belt of energetic charged particles encircling the planet. Its scale is extraordinary. The torus extends across a region roughly 6 Jupiter radii wide. Since Jupiter itself is enormous, the resulting structure dwarfs entire planetary systems of activity elsewhere in the solar system. Yet, despite its size, it remains invisible to human eyes under ordinary conditions. In ultraviolet light, however, it glows. Long before spacecraft reached Jupiter, astronomers detected evidence of this strange ring from Earth. Observations revealed emissions that hinted at energetic material orbiting the giant planet. Later, instruments aboard Voyager confirmed its existence directly, transforming an unusual observation into a measurable physical structure. But size alone is only part of the story. The plasma within the torus reaches temperatures of tens of thousands of degrees. At such energies, atoms behave very differently from ordinary gases. Electrons move freely. Magnetic forces dominate motion. The environment becomes one of the most energetic regions in the outer solar system. Io continuously feeds it. When volcanic activity increases, more material enters space. The torus responds. Its brightness changes. Its density shifts. New particles circulate through the system. Astronomers can observe these variations from Earth and use them as clues about conditions on a moon hundreds of millions of kilometers away. Think about that for a moment. A volcanic eruption on a distant moon can alter the appearance of a magnetic structure surrounding a giant planet. By studying the larger structure, scientists gain insight into events occurring far below on the surface that produced it. The connection is remarkably direct. Sodium provides one of the most dramatic examples. Escaping sodium atoms have been traced millions of kilometers from Jupiter, creating a diffuse cloud that spreads across much of the Jovian system. The material becomes a marker, revealing how far Io's influence extends. But the torus itself remains only one chapter in a larger interaction. Charged particles trapped within Jupiter's magnetic field continue exchanging energy with the planet and with the moon that supplies them. The relationship transforms Io from a simple satellite into an active participant in shaping the environment of the entire Jovian system. Imagine two worlds linked by an invisible current, stretching across hundreds of thousands of kilometers of space. No metal wire exists between them. No engineered machine maintains the connection. Yet energy flows continuously. Io and Jupiter are bound together by electricity. The process begins with motion. Jupiter rotates extraordinarily fast, completing one rotation in roughly 10 hours. Io moves much more slowly, requiring nearly 42 hours to complete a single orbit. Because of that difference, Jupiter's magnetic field constantly sweeps past the Moon. The interaction resembles a conductor moving through a magnetic generator. As magnetic field lines rush across Io, electrical charges within the Moon's surrounding environment become separated and accelerated. A voltage develops. Current begins to flow. The resulting pathway follows Jupiter's magnetic field lines through a structure known as the Io flux tube. This is not an abstract concept. It is a genuine electrical circuit operating in space. Measurements indicate that roughly 5 million amperes of electrical current travel along this connection. The number is difficult to visualize because almost no human experience provides a useful comparison. Even among planetary phenomena, the scale stands apart. The energy involved is equally astonishing. Scientists estimate that approximately 2 trillion watts are dissipated through the system. That figure exceeds the electrical generation capacity of many nations combined, yet no power station exists. No technology is required. Orbital motion, volcanic material, and magnetic forces provide everything needed. But the current does not simply vanish into space. It follows magnetic pathways toward Jupiter itself. Eventually, charged particles strike the giant planet's upper atmosphere. Energy is deposited there, exciting atmospheric gases and producing brilliant auroral emissions near the poles. These auroras are permanent features. Unlike many auroras that brighten and fade with changing conditions, the ones associated with Io remain continuously present because the electrical connection itself never stops. As Io moves through its orbit, the brightness and position of these emissions change in predictable ways. Power leaves one world and appears on another. Observations from the Hubble Space Telescope have revealed these luminous regions directly. They appear as bright spots embedded within Jupiter's larger auroral system. Their behavior matches the orbital rhythm of Io, confirming the connection across space. The story grows even more intricate. Researchers have identified additional auroral footprints trailing behind the primary spot. These secondary features arise from Alphane waves, a type of magnetic disturbance that travels through electrically conducting plasma. The waves reflect and propagate along the flux tube, creating multiple glowing signatures in Jupiter's atmosphere. What appears as a collection of separate phenomena is actually one uninterrupted chain. Deep within Io, tidal forces generate heat. That heat powers volcanic eruptions. Volcanic material feeds the plasma torus surrounding Jupiter. The torus supplies charged particles to the magnetic environment. The magnetic environment drives electrical currents through the flux tube. Those currents ultimately illuminate Jupiter's polar skies. Every link depends on the others. Across 4.5 billion years, the system has continued operating, transforming gravity into heat, heat into plasma, plasma into electricity, and electricity into light. What we observe is not a collection of isolated events, but a single planetary machine extending across an entire corner of the solar system. Some places in the solar system challenge our intuition. Io challenges our definition of survivability. As we follow its orbit around Jupiter, we find that the moon does not merely coexist with a powerful magnetic environment. It lives inside one of the most energetic radiation regions known anywhere beyond the sun itself. Jupiter's magnetosphere, the vast magnetic bubble surrounding the giant planet, is so enormous that if human eyes could perceive it from Earth, it would appear larger than the full moon in our sky. Within that immense structure lies a particularly dangerous zone. Io travels directly through it. The radiation intensity at the moon's surface reaches approximately 3,600 sieverts every day. Numbers alone struggle to communicate what that means. A dose of roughly 5 sieverts is generally considered lethal for a human being. At Io, that amount accumulates in about 33 minutes. The environment is relentless. Charged particles race through space at tremendous energies, trapped and accelerated by Jupiter's magnetic field. They strike the moon continuously, penetrating exposed surfaces and transferring energy into everything they encounter. No atmosphere exists there with enough thickness to provide meaningful protection. Machines suffer as well. The Galileo spacecraft was specifically designed to operate within the Jovian system. Its electronics incorporated extensive radiation protection developed with this hazard in mind. Even so, repeated exposure gradually damaged onboard systems. During the mission, cumulative radiation effects permanently degraded the spacecraft's camera after multiple encounters near Io. But radiation does more than threaten visiting spacecraft. It actively reshapes the moon itself. When energetic particles strike sulfur dioxide molecules on the surface, chemical bonds are broken apart. New compounds form through reactions that rarely occur under ordinary planetary conditions. Among the products are sulfur trioxide and other unusual sulfur-bearing materials. The surface becomes a continuously evolving chemical laboratory driven by radiation rather than sunlight. Atoms are removed as well. A process called ion sputtering occurs when incoming particles physically knock atoms away from the ground. Material is ejected into space, one atom at a time. Over long periods, this steady erosion contributes to the escaping matter that feeds the vast plasma environment surrounding Jupiter. The moon is being altered constantly. Imagine standing on such a surface, if standing there were somehow possible. Every moment, energetic particles would pass through your body. Molecular structures would be disrupted almost immediately. Deoxyribonucleic acid, the molecule carrying genetic information in terrestrial life, would accumulate damage faster than any known biological repair system could respond. Minutes would matter. Recent exploration has shown that the challenge remains just as severe today. During close approaches in 2023 and 2024, the Juno spacecraft carefully managed observation times and flight geometry to reduce cumulative radiation exposure. Modern shielding helps, but limits remain. What makes this environment especially remarkable is its connection to everything else we have seen. The orbital resonance maintaining Io's path generates internal heating. That heating powers volcanism. The same orbital position places the moon deep within Jupiter's radiation belts. The force responsible for its extraordinary activity is also responsible for its extraordinary danger. The thing that makes Io burn is the same thing that makes it lethal. A long arc through the inner solar system eventually carried a spacecraft toward the giant planet that had dominated so much of our story. By the time Galileo arrived at Jupiter in December of 1995, it had already spent 6 years crossing space after launching from Earth. Its destination was historic. No spacecraft had ever entered orbit around a gas giant before. The achievement changed planetary science. For nearly 8 years, Galileo remained within the Jovian system, watching its moons from changing distances and perspectives. During that time, Io repeatedly emerged as one of the mission's most astonishing targets. The spacecraft completed 6 dedicated close flybys of the moon, each one threading through an environment that challenged both engineering limits and scientific expectations. Some passes were remarkably close. The nearest approach carried Galileo only 162 kilometers above the surface, which is about 101 miles. At that distance, broad volcanic provinces gave way to individual structures, distinct lava flows, and detailed geological features that earlier observations could never resolve. The discoveries accumulated quickly. More than 100 thermal hotspots were confirmed across the moon. Surface maps reached levels of detail previously unimaginable. Measurements of gravity provided crucial clues about the hidden interior beneath the constantly changing crust. Each encounter added another piece to a puzzle that had begun with the Voyager missions years earlier. But one result stood apart. Galileo carried an infrared spectrometer, an instrument designed to measure heat by detecting infrared radiation. When it observed some of Io's hottest eruptions, the temperatures appeared so extreme that portions of the data exceeded the calibration range built into the instrument. Scientists found themselves confronting a strange problem. The moon was producing conditions beyond what their own measurement system had been designed to handle. New analytical methods became necessary. Researchers developed techniques to estimate eruption temperatures from incomplete signals, extracting information from data that initially seemed unusable. The effort revealed volcanic processes operating at intensities rarely imagined before the mission began. Yet Galileo faced another challenge entirely. Its main high-gain antenna, intended to transmit information back to Earth at high speed, failed to deploy correctly. The spacecraft was forced to rely on a much smaller, low-gain antenna. Data flowed home at roughly 1/3000th of the planned rate. Every transmission mattered. Engineers and scientists responded with extraordinary creativity. Compression software was rewritten. Observation priorities became increasingly strict. Valuable information had to be selected carefully before beginning its journey across roughly 780 million kilometers, which is about 485 million miles, of space. Important choices were unavoidable. Despite those limitations, the mission transformed our understanding of Io more profoundly than any investigation before it. The moon emerged as a dynamic world of ongoing geological activity rather than a frozen relic of ancient history. When Galileo's mission finally approached its end in September of 2003, another decision reflected the growing awareness of potentially habitable environments elsewhere in the Jovian system. Mission planners directed the spacecraft into Jupiter's atmosphere rather than allowing an uncontrolled future impact with Europa. The concern was planetary protection, preventing any surviving Earth microorganisms from reaching a moon that may conceal a subsurface ocean. Galileo disappeared into Jupiter, but the knowledge it returned continued reshaping how we see Io long after the spacecraft itself was gone. For 2 decades, Io remained at a distance. Powerful telescopes continued watching from Earth, and occasional spacecraft glimpses added scattered observations. Yet no mission ventured close enough to provide the kind of detailed inspection that Galileo had once achieved. The moon continued changing, volcanoes continued erupting, entire regions evolved beyond the reach of direct scrutiny. Then the long gap ended. In December of 2023, and again in February of 2024, the Juno spacecraft swept past Io during two carefully planned encounters. Juno had been designed primarily to investigate Jupiter itself, yet these flybys offered an opportunity too valuable to ignore. The spacecraft approached to roughly 1,500 kilometers above the surface, which is about 932 miles, providing the closest views obtained in more than 20 years. The images were extraordinary. Features that had remained unresolved for decades suddenly sharpened into view. Fresh geological details appeared across landscapes already known to be active. More importantly, the observations confirmed that volcanic activity was occurring simultaneously at dozens of separate locations. The moon remained fully alive. Juno carried an infrared instrument called Jovian Infrared Auroral Mapper, an instrument that measures heat by detecting infrared radiation. During both encounters, it identified numerous thermal hotspots scattered across the surface. Some belonged to volcanoes already familiar from earlier studies. Others appeared within regions that had shown comparatively little activity in previous observations. New patterns emerged. One particularly intriguing discovery came from a large lava lake near the North Polar region. The surface appeared remarkably smooth, displaying a reflective quality unlike the rough terrain surrounding it. Scientists interpreted this appearance as evidence of a broad molten pool resting between major overturning episodes, covered by a thin, solid crust capable of reflecting light with unusual uniformity. The scene hinted at ongoing processes beneath. Additional observations revealed what may be a previously uncharacterized volcanic structure. At the time these findings were reported, researchers were still examining the data in detail, comparing the new measurements against decades of earlier observations. Questions remained open. The mission's design provided another advantage. Because the two flybys occurred approximately 60 days apart, scientists gained a rare opportunity to compare the same regions across a relatively short interval. Surface changes that would be invisible on most worlds became measurable on Io. Volcanic deposits shifted, thermal signatures evolved, certain locations displayed unmistakable differences between visits. The moon changed quickly enough to watch, yet approaching Io remained a hazardous undertaking. Jupiter's radiation environment continued imposing strict limits on spacecraft operations. Juno's radiation-hardened systems allowed it to survive encounters that would destroy conventional electronics, but every close approach carried a cost. Mission planners carefully managed instrument usage and trajectory design because each flyby consumed part of the spacecraft's finite radiation tolerance. Even successful observations required caution. What Juno returned was more than a collection of images. The mission provided fresh measurements of an active world that had spent 20 years beyond close inspection. Those data are now helping engineers and planetary scientists define the requirements, instruments, and priorities for future missions that may someday study Io in even greater detail. After decades of spacecraft encounters, telescope campaigns, laboratory experiments, and theoretical modeling, Io still guards some of its most important secrets. The moon has revealed extraordinary processes, yet several of the biggest questions remain unresolved. Some concern details. Others concern the entire framework of how the world functions beneath its surface. At the center of the debate lies a surprisingly simple question. Does Io possess a global magma ocean? Current measurements suggest the possibility of a widespread layer of molten rock beneath the crust. Electrical conductivity data support that interpretation, yet the evidence stops short of confirmation. Scientists can model such an ocean, and many observations fit the idea remarkably well. but alternative explanations remain viable. To settle the issue, researchers need more precise measurements of gravity and magnetic field interactions collected during repeated close passes. The uncertainty extends deeper. How does heat actually travel from the interior to the surface? Two major explanations compete. One proposes that heat moves through concentrated volcanic conduits, narrow pathways carrying energy upward into specific regions. The other favors broad mantle convection, a process in which large volumes of hot material slowly circulate through the interior. Both models explain parts of the available evidence. Neither explains everything. The distinction matters. Understanding the transport mechanism determines how volcanic worlds evolve through time and how efficiently rocky bodies release internal energy. That question reaches far beyond Io itself. Another mystery glows within the lava. Some eruptions appear hot enough to resemble komatiites, an ancient volcanic rock type associated with Earth's distant past. Yet, scientists still lack definitive measurements of the chemical composition of Io's hottest lavas. Determining that composition requires either direct sampling or spectroscopic observations far more detailed than those currently available. The answers remain out of reach. History introduces another layer of uncertainty. Tidal heating has operated since the early solar system, but nobody knows whether Io's volcanic intensity has remained stable across billions of years. Perhaps the activity has fluctuated dramatically. Perhaps long periods of relative calm alternated with intervals of extreme eruption. Existing evidence cannot reconstruct the complete story. Large eruptions raise additional puzzles. Researchers continue examining whether massive Pallanian eruption events can trigger activity elsewhere. The remarkable sequence observed during 2013, when multiple major eruptions occurred within a relatively short interval, hints at possible connections between distant volcanic systems. But the mechanism remains unknown. Future missions are designed with these questions in mind. One proposed mission, called Io Volcano Observer, would perform repeated close flybys while measuring gravity, magnetic responses, heat flow patterns, and plume chemistry. Such observations could reveal details that current datasets cannot provide. A particularly important measurement involves the tidal love number, a quantity describing how much a world changes shape under gravitational stress. By measuring Eo's deformation with high precision, scientists could place powerful constraints on the magma ocean question. The mission concept also includes a mass spectrometer, an instrument capable of identifying gases directly from volcanic plumes during close passes. If flown, it would provide the first direct chemical sampling of an eruption on Io. As we follow these unanswered questions, you begin to see that Io is more than a volcanic moon. It is a laboratory for understanding how rocky worlds generate, transport, and release heat, knowledge that may ultimately help us interpret countless distant planets scattered throughout the galaxy. Some worlds help us understand themselves. A much smaller group helps us understand our own past. As we follow the heat rising through Io's crust, we begin to encounter a strange possibility. This moon may function as a geological time machine. The connection begins with a rare kind of lava. The hottest eruptions observed on Io resemble komatiitic volcanism, a style of eruption associated with Earth's distant youth. Komatiites formed when Earth's mantle was far hotter than it is today, producing exceptionally fluid lava capable of moving rapidly across the landscape. Most known examples on Earth formed between roughly 3.5 billion and 2.5 billion years ago during the Archean era. That world no longer exists. Earth's interior gradually cooled across immense spans of time. The conditions that once generated widespread comatotic eruptions faded away. What remains today is an incomplete record preserved within ancient rocks that have endured burial, deformation, chemical alteration, and erosion. Many details vanished long ago, but Io continues producing similar eruptions in the present. Scientists can observe them directly, estimate their temperatures, monitor their evolution, and compare their behavior with ancient geological evidence preserved on Earth. Instead of reconstructing the process from fragments, we can watch an active version unfolding. The comparison grows deeper. Early Earth was an intensely volcanic world. Large regions may have been resurfaced repeatedly by immense outpourings of molten rock. Geological stability was far less established than it is today. Impact scars disappeared beneath new material. Fresh crust formed continuously. Internal heat dominated the landscape. Much of that sounds familiar. Io experiences comparable renewal on a scale unmatched elsewhere in the modern solar system. Surface features are buried, altered, and replaced so frequently that ancient records rarely survive. In both cases, volcanism acts as a primary architect of the environment. Some researchers have even explored another intriguing connection. During Earth's earliest history, the Moon orbited much closer than it does today. Gravitational interactions would have been stronger. Tidal effects may have contributed additional internal heating, although the exact magnitude remains uncertain. If that influence proved significant, the comparison becomes even more compelling. Io's activity is powered by tidal heating operating at extraordinary intensity. The Moon demonstrates what sustained gravitational energy can accomplish inside a rocky body. By studying those effects in detail, scientists gain clues about processes that may once have shaped portions of Earth's early development. Chemistry adds another layer. Sulfur compounds play a major role across Io's surface and atmosphere. Similar sulfur-rich environments existed on the young Earth before modern biological and atmospheric systems transformed the planet. Volcanic gases, temperature gradients, and chemical reactions created conditions very different from those surrounding us today. Here we arrive at a larger question. If intense volcanism, sulfur chemistry, and powerful energy gradients formed part of the environment that preceded life on Earth, what can a living example of those conditions still teach us? Io itself shows no evidence of biology. The radiation environment alone makes the surface extraordinarily hostile. Yet the Moon preserves processes that may resemble chapters from Earth's earliest story. In that sense, Io is more than a distant volcanic world. It is a surviving demonstration of geological conditions our own planet left behind billions of years ago. Seen from afar, Io and Europa appear to occupy neighboring lanes around Jupiter. Their orbital paths are separated by only about 260,000 kilometers, which is about 162,000 miles. Yet, beneath their surfaces, these two worlds represent opposite outcomes of the same underlying force. Both are shaped by tidal heating. Both are stretched by Jupiter's gravity. Both participate in the orbital resonance that has guided their evolution for billions of years. But the energy delivered to each moon follows very different paths. On Io, tidal heating is pushed toward an extreme. Internal friction generates enough energy to keep portions of the interior partially molten. Heat escapes through relentless volcanism. The surface changes constantly. Fresh lava buries older terrain. Geological renewal never truly pauses. Europa followed another route. There, tidal heating remains strong enough to prevent complete freezing, yet weak enough to avoid widespread melting of the outer shell. Beneath the ice lies a global ocean of liquid water. Current estimates place the ice shell at roughly 15 to 25 kilometers thick, which is about 9 to 16 miles, while the ocean below may extend between 60 and 150 kilometers deep, which is about 37 to 93 miles. The scale is astonishing. That hidden ocean likely contains more water than all of Earth's oceans combined. Protected beneath ice, isolated from direct exposure to space, it may have remained liquid for immense spans of time. By the standards of biological history on Earth, that provides a remarkably long opportunity for chemistry to unfold. But Europa does not maintain those conditions alone. The same orbital resonance that sustains Io's eccentric path also helps preserve Europa's. Each moon participates in a larger gravitational arrangement. Remove one component, and the balance changes. Without Io occupying its position in the chain, Europa would experience weaker tidal flexing. Internal heating would decline. Over long periods, the ocean could begin moving toward a colder state. The connection extends beyond gravity. Material launched from Io's eruptions does not remain confined to its source. Sulfur compounds eventually migrate through Jupiter's environment and reach Europa's surface. Those deposits introduce chemical ingredients and energy sources that researchers must consider when evaluating Europa's potential habitability. A frozen shell receives gifts from a volcanic neighbor. For this reason, scientists studying Europa cannot treat it as an isolated ocean world. Models must account for Io's contributions. The moon serves as a supplier of sulfur, a stabilizer within the resonance system, and an indirect regulator of heat across the inner Jovian environment. Modern exploration reflects that reality. The Europa Clipper mission, launched in October 2024, will focus primarily on Europa through dozens of planned flybys. Yet, several observations will also examine Io and the surrounding plasma environment. Investigators increasingly view these moons as parts of a connected system rather than separate destinations. That perspective changes the story. When we search for places where life might emerge, attention naturally turns toward Europa's hidden ocean. But the conditions keeping that ocean active are linked to a neighboring moon covered in volcanoes. Io may never be considered habitable. Its role is different. It supplies energy, chemistry, and orbital stability, helping maintain one of the most intriguing environments in the outer solar system. Far beyond Jupiter's orbit, the same physical process continues its work on other worlds. Gravity stretches, orbits flex, internal friction generates heat. What we witness on Io is an extreme expression of a mechanism that appears throughout the cosmos. The principle is surprisingly simple. When a moon or planet follows a slightly elongated path, changing gravitational forces repeatedly squeeze and relax its interior. Rock bends, ice deforms, energy becomes heat. On Io, that heat erupts through volcanoes. Elsewhere, it follows different routes. One of the most compelling examples circles Saturn. Enceladus is a relatively small moon, yet tidal heating prevents its interior from freezing completely. Beneath an icy shell lies a global ocean of liquid water. Through fractures near the South Pole, material from that hidden ocean escapes into space as towering plumes of water vapor and ice grains. The Cassini spacecraft transformed our understanding of those eruptions. During repeated flybys, Cassini passed directly through the plumes and sampled their contents. Instruments detected organic molecules, molecular hydrogen, and tiny silica particles. Molecular hydrogen is especially important because it can be produced when hot water interacts with rock on the ocean floor. Silica particles point toward similar hydrothermal activity. Deep water, warm rock. The ingredients suggest an active environment beneath the ice, maintained by the same tidal process that drives activity elsewhere. Another Saturnian world presents a different variation. Titan possesses a thick atmosphere rich in hydrocarbons, compounds built from hydrogen and carbon. Tidal interactions contribute energy to Titan's interior and influence its long-term evolution, while sunlight and atmospheric chemistry create rivers, lakes, and weather systems unlike anything found elsewhere in the solar system. But the significance of tidal heating grows even larger once we look beyond our planetary neighborhood. Many stars in our galaxy are red dwarfs, small and relatively cool stars that vastly outnumber stars like our Sun. For a rocky planet to receive enough warmth for liquid water, it must orbit very close to such a star. Those close distances amplify gravitational effects. The consequences can be dramatic. A planet may occupy the traditional habitable zone while simultaneously enduring intense tidal heating. Volcanoes could dominate the surface. Crustal recycling might become relentless. Stable oceans could struggle to persist despite favorable temperatures from starlight alone. In some cases, the result may resemble Io more than Earth. Researchers have also explored another possibility. Giant planets orbiting far from their stars could host moons warmed primarily by tidal heating. Such worlds might maintain liquid water even where sunlight provides little energy. Habitability, in that scenario, depends less on distance from a star and more on orbital architecture. This idea has inspired the concept of a tidal habitable zone, a range of conditions where gravitational heating remains strong enough to support liquid water, yet moderate enough to avoid catastrophic geological extremes. Every model begins somewhere. For tidal heating, that starting point is Io. It remains the one place where we can directly observe this process operating at extraordinary intensity. Measurements gathered there allow scientists to test theories, refine calculations, and extend those lessons outward to countless worlds scattered across the galaxy, many of which may be experiencing similar forces at this very moment. Nothing about Io is fixed forever. Even the immense forces that shape it today belong to a story still unfolding, a story measured not in centuries or civilizations, but in billions of years. As we watch eruptions brighten its surface and tidal forces flex its interior, we are seeing a single frame from an extraordinarily long sequence. The system that powers Io has remained remarkably stable throughout most of solar system history, yet stability and permanence are different things. At the heart of that future lies the orbital relationship linking Io, Europa, and Ganymede. This gravitational arrangement, known as the Laplace resonance, has endured for roughly 4.5 billion years. During that immense span, it has continuously maintained the slight orbital distortion that allows tidal heating to operate. But orbital systems evolve. Every orbit transfers tiny amounts of energy and angular momentum between Jupiter and its moons. The changes are extraordinarily slow. Human history is far too brief to notice them. Even entire geological eras pass with little visible difference. Yet over billions of years, those small adjustments accumulate. As orbital parameters gradually shift, the resonance may eventually weaken or change. If that happens, Io's orbit would become more circular. The continual stretching and squeezing of its interior would lessen, heat production would decline, the transformation would not be sudden. Volcanic activity would fade over immense spans of time. Eruptions would become less frequent. Internal melting would decrease. Regions that are now constantly renewed by lava could persist for longer intervals before being resurfaced again. The great engines would ease. Current estimates suggest these changes occur on timescales measured in billions of years. For a very long future, Io is expected to remain active, long after continents on Earth have shifted beyond recognition, and long after many familiar landscapes have vanished, volcanoes may still be erupting across Io's surface. Another future event looms even farther ahead. In approximately 5 billion years, the Sun will exhaust the hydrogen fuel in its core and expand into a red giant star. The outer solar system, currently locked in deep cold, will experience dramatically increased sunlight. Today, many of Jupiter's moons average temperatures near minus 150 degrees Celsius or minus 238 degrees Fahrenheit across their sunlit regions. During the red giant phase, those conditions could change substantially. Europa may experience especially significant effects. Its subsurface ocean already exists beneath ice. Additional solar heating could alter the thickness of that ice shell and influence the movement of energy through the moon's outer layers. Throughout that transition, Io would continue contributing material to the Jovian system. Sulfur compounds, plasma, and volcanic gases would remain part of the broader environment surrounding Jupiter, influencing neighboring worlds as conditions slowly evolve. Yet traces of Io's past may outlast its future activity. For billions of years, volcanic products have entered surrounding space, leaving chemical fingerprints throughout the system. Some are preserved in Jupiter's plasma environment. Others may be recorded on nearby moons. Together, they form a vast historical archive, a planetary autobiography written across an entire family of worlds, waiting for us to learn how to read every chapter. Imagine arriving at a place where motion and stillness exist side by side, each dominating a different part of the landscape. That contrast defines Io more than any statistic ever could. Across much of the surface, nothing appears to move. There is no meaningful weather, no drifting clouds, no rain, no changing seasons. Io's axial tilt is less than 0.04 degrees, so sunlight changes very little throughout its year. The atmosphere is far too thin to support anything resembling the winds we know on Earth. Only subtle processes remain. Sulfur dioxide slowly shifts from place to place as temperatures change. Volcanic gases emerge from active regions and settle elsewhere. Frost forms and disappears. These motions unfold gradually, almost beyond perception. Stand far from an eruption center, and you would find yourself surrounded by frozen plains coated in sulfur compounds. Low hills stretch across the horizon. Volcanic scars cut through the landscape. Above them, occasional plumes rise to extraordinary heights. Yet no sound would reach you. The atmosphere lacks the density required to carry sound over meaningful distances. Explosions powerful enough to reshape landscapes would unfold in complete sensory isolation. Vast eruption columns would climb skyward. Lava fountains would burst from fissures. None of it would produce an audible roar. You would only watch. Above this strange terrain hangs the dominant feature of the sky. Jupiter appears approximately 36 times wider than Earth's moon. Its striped cloud bands remain visible without assistance. Storm systems larger than planets drift across its face. From Io, the giant world occupies an enormous portion of the heavens, an ever-present reminder of the gravitational force controlling everything around you. The view changes further after local darkness arrives. Jupiter reflects enough sunlight to illuminate the surface below. Sulfur fields remain visible beneath a dim glow. Plateau edges cast shadows. Craterless plains take on muted colors. The landscape never becomes completely dark while Jupiter stands overhead. Some regions generate their own light. Loki Patera stretches roughly 202 kilometers across, which is about 126 miles. During active periods, portions of the lava lake radiate a faint orange glow. From hundreds of kilometers away, which is about 62 miles, molten surfaces could remain visible against the surrounding darkness. The effect would feel strangely unreal. A frozen plain, a glowing horizon, a giant planet dominating the sky. But another reality would remain hidden. Radiation continually pours through the environment. Charged particles sweep across the surface. Chemical reactions alter exposed materials. Energy accumulates within anything unfortunate enough to remain there. You would see volcanic violence unfolding on a planetary scale. You would witness eruptions capable of transforming entire regions. Yet two human senses would offer little guidance. No sound would accompany the spectacle, and no movement in the air would hint at danger. Everything appears motionless. Everything is changing. Under Jupiter's immense gaze, fire and stillness coexist on the same world, creating a landscape unlike any other known place in the solar system. There is a habit in the way we describe places like Io. We call them violent worlds. The word arrives naturally because the surface appears dominated by eruption, collapse, fracture, and fire. Yet, the closer we look, the less that description seems to fit. Violence suggests disorder. It suggests unpredictability, instability, and events unfolding without pattern. Io offers something very different. Beneath every plume and lava field lies a system governed by remarkable consistency, one that has operated for billions of years with extraordinary reliability. Every eruption follows from it, every mountain pushed upward, every volcanic depression that expands, every wave of molten rock moving through Loki Patera, every particle feeding Jupiter's surrounding plasma environment. Each phenomenon traces back to the same underlying mechanism. Three moons remain locked together. The orbital relationship linking Io, Europa, and Ganymede continues to operate with astonishing precision. Astronomers call this arrangement the Laplace resonance. A resonance is a repeating gravitational rhythm in which orbital periods remain mathematically connected. Io circles Jupiter 4 times, while Europa completes 2 orbits and Ganymede completes 1. The pattern endures. Over immense spans of time, the resonance has remained one of the most stable known configurations in the solar system. It has not drifted far from its present form. It has not unraveled. Instead, it continually supplies the slight orbital distortion required to flex Io's interior and generate heat. From the surface, none of that is obvious. You see collapsing terrain and advancing lava flows. You see regions transformed by eruptions. You see landscapes that appear restless and destructive. But those visible changes are simply the outward expression of an energy system functioning exactly as physics predicts. Nature often works this way. Many of the most dramatic phenomena we observe emerge from deep stability rather than disorder. A star appears turbulent when viewed from afar, yet its energy production depends on a delicate balance between gravity and nuclear fusion. That balance can persist for billions of years. The same principle appears on Earth. A hurricane may look chaotic from space, but it follows understandable physical rules. It redistributes heat through the atmosphere. Pressure differences drive circulation. Energy moves from one state toward another. Beneath the swirling clouds lies structure. Io belongs in that tradition. Its volcanism is the visible exhaust of a gravitational engine. Orbital energy enters the system. Internal friction converts that energy into heat. Molten material rises. The surface responds. The process repeats again and again. What we call violence may sometimes mark the moment when hidden energy becomes visible. Deep processes remain unnoticed for ages, then reveal themselves through light, motion, heat, or change. Our attention is drawn to the eruption because it can be seen, while the underlying mechanism remains concealed. Io reminds us of that distinction. The moon burns because the mathematics demand an outlet. Heat escapes because energy continues to arrive. Fire becomes evidence of balance rather than failure. Seen from that perspective, the glowing plains and towering plumes take on a different character. Under the darkness of space, Io's fires are not signs of chaos. They are proof that an ancient gravitational clock is still keeping perfect time. When we encounter a world as extreme as Io, our first instinct is often comparison. We hold it beside Earth and measure the differences. We call it hostile. We call it destructive. Sometimes we reach for words drawn from human experience and describe it as a place of torment or warning. But those words belong to us. Io has no awareness of its eruptions. It does not witness its lava lakes. It does not experience the radiation that sweeps across its surface. The moon is neither cruel nor tragic. It is simply the outcome of mass, gravity, distance, and motion interacting over immense spans of time. Physics does not judge. What we perceive as violence is often a layer of interpretation placed upon a process that exists independently of human meaning. From our perspective, mountains collapsing and lava spreading across vast plains appear dramatic, yet to the underlying laws governing the system, these events are merely consequences, nothing more. Seen from that angle, Io becomes less a spectacle and more a revelation. It exposes planetary processes in unusually direct form. Many of the mechanisms shaping Earth remain hidden beneath oceans, buried within crustal plates, or moderated by an atmosphere that redistributes energy across the globe. Earth is buffered. Water absorbs heat. Weather circulates it. Plate tectonics release pressure through pathways refined across billions of years. Biological systems interact with atmospheric chemistry. Countless feedback loops soften extremes and maintain conditions that feel familiar to us. Io possesses almost none of those comforts. There is no global ocean smoothing thermal contrasts. There are no moving tectonic plates regulating interior stresses. There is no substantial atmosphere spreading energy around the planet. What remains is a world where fundamental forces reveal themselves with unusual clarity. The machinery is exposed. Looking at Io can feel like stripping away layers from a complex device until only the engine remains. Heat enters through gravitational interactions. Internal friction converts that energy into molten rock. Volcanism releases the accumulated energy back into space. The chain is direct, visible, and difficult to ignore. Yet the most interesting consequence emerges beyond Io itself. Its eruptions help populate Jupiter's surrounding environment with chemically active material. Its position helps sustain the orbital resonance that influences neighboring moons. The energy flowing through the system contributes to conditions that may help maintain Europa's long-lived ocean beneath its frozen exterior. Connections appear everywhere. What seems destructive at one scale becomes constructive at another. Material lost from Io becomes part of a larger network. Heat generated within one moon affects the dynamics of others. Individual processes combine into a system whose behavior cannot be understood through any single world alone. That perspective changes the meaning of violence. The eruptions are real, the temperatures are real, the radiation is real. But those phenomena participate in a structure that creates continuity, transfers energy, and maintains balance across an entire planetary neighborhood. We often imagine life enduring despite the universe's harshness. Io offers a different possibility. The same forces that appear overwhelming in one place may create opportunity elsewhere. Energy drives chemistry. Chemistry creates complexity. Complexity opens pathways that would otherwise remain closed. In that sense, the fire is not separate from the order. It is one of the ways order is made visible. A useful place to begin is with a number. At favorable alignment, Io lies roughly 628 million kilometers from Earth, which is about 390 million miles. Across that distance, we have measured the temperatures of individual lava lakes. We have identified the chemistry of volcanic plumes rising above specific regions. We have even tracked the progress of lava overturning across Loki Patera and estimated that a complete circuit can require about 540 days. That is an astonishing thing. The distance alone pushes beyond ordinary experience. Light itself requires more than half an hour to travel between Earth and Jupiter when the planets are widely separated. Yet details from Io reach us with enough precision to reveal processes unfolding across landscapes we have never touched. Knowledge crossed the gap. For centuries after Galileo first recorded Jupiter's 4 large moons in January 1610, Io remained little more than a moving point of light. Generations of observers watched it circle Jupiter without knowing what kind of world it truly was. The surface remained hidden. Then the pace changed. Within roughly 45 years, beginning with the age of planetary spacecraft, Io transformed from a distant dot into one of the best studied geological environments beyond Earth. Volcanoes were discovered, temperatures were measured, mountains were mapped, entire systems of energy transfer became visible. The transformation came through instruments. Cameras converted reflected light into images. Spectrometers separated light into its component wavelengths, allowing scientists to identify materials from afar. Magnetometers measured magnetic fields. Gravity experiments revealed clues about unseen interiors. Each device extended a particular human sense far beyond the limits of the body. Metal became curiosity. Those instruments traveled into regions no person has visited. They crossed millions of kilometers carrying questions designed on Earth and returned carrying fragments of answers. Every measurement depended on years of planning, testing, engineering, and patience. The chain behind each discovery is surprisingly long. Someone proposed a mission, others approved funding. Engineers designed hardware capable of surviving launch, vacuum, radiation, and time. Scientists developed experiments. Technicians assembled components. Teams monitored spacecraft for years while they crossed the solar system. Then data arrived. A decision made in an office could eventually lead to an image appearing on a computer screen, revealing a volcanic plume rising above a sulfur-coated plain hundreds of millions of kilometers away. The connection feels improbable, yet it happens repeatedly. But the most remarkable part may not be technological. The effort required to understand Io produces no immediate necessity. Knowing the temperature of a distant lava lake does not feed a city. Measuring the chemistry of a volcanic plume does not solve most daily problems. The value comes from understanding itself. That impulse appears again and again throughout history. You can trace it backward through observatories, expeditions, laboratories, and libraries. It appears whenever people choose to investigate something simply because it exists and can be known. The same thread reaches back to Galileo. In January 1610, he carefully recorded four small points of light moving beside Jupiter. He could not know where that observation would lead. Yet the impulse was already there, the willingness to look closely, preserve the evidence, and follow the question wherever it might go. Across the centuries, that question eventually arrived at Io. Sometimes the path back to Earth begins somewhere unexpected. It is tempting to treat Io as a distant curiosity, a volcanic moon circling a giant planet far beyond the region where human history unfolded. Yet, many of the ideas that help explain our own existence pass directly through places like this. The story seems remote at first. Then the connections begin to appear. One link leads to Europa. The gravitational resonance binding Jupiter's major moons together continues to supply energy throughout the system. That same resonance that stretches and heats Io also helps sustain the interior warmth of Europa. Beneath Europa's frozen surface lies a vast liquid ocean, one of the most promising environments for life beyond Earth within our solar system. The relationship is inseparable. Remove the resonance and the balance changes. Alter the balance and the heating changes. The ocean becomes a different place. A moon famous for fire helps preserve a moon famous for water. The pattern reaches farther. Many researchers believe tidal forces played a greater role during Earth's distant past than they do today. Early in solar system history, our moon orbited much closer to Earth. Stronger tides moved immense quantities of energy through the planet's oceans and crust. The exact consequences remain debated, but the underlying physics is familiar. Gravity reshapes worlds. The connection becomes even more striking when we examine Earth's earliest geology. Io continues to produce extremely hot volcanic eruptions, resembling the komatitic volcanism that characterized portions of the ancient Earth. Those eruptions created intense thermal gradients and chemically diverse environments across young planetary surfaces. Conditions mattered. Before biology emerged, chemistry needed places where energy flowed and reactions could occur. Ancient volcanic environments provided those opportunities. While no one can point to a single eruption and declare it responsible for life's origin, many of the ingredients associated with prebiotic chemistry, meaning chemistry that exists before life, were present in such settings. Io preserves a version of that world. What vanished from Earth billions of years ago remains active there today. The moon offers a living example of processes that once helped shape our own planet during an era from which only fragments remain. But the implications extend beyond the solar system. Astronomers now recognize tidal heating as a common planetary process. Wherever moons and planets interact through gravity, energy can be generated internally. Around distant stars, similar mechanisms may be warming icy worlds, driving geology, and sustaining chemical environments far from direct stellar heat. The principle is universal. That makes Io more than a moon orbiting Jupiter. It becomes a reference point, a place where we can directly observe the relationship between gravity, geology, chemistry, and planetary evolution. By understanding one world in detail, we gain tools for interpreting countless others. The universe is neither uniformly welcoming nor uniformly barren. Some environments become hostile because of the very forces that make neighboring environments possible. Jupiter's gravity helps create Io's volcanic intensity. That same system contributes to Europa's long-lived ocean. The chain continues outward and backward through time. Follow it far enough and it reaches us. A sequence of gravitational relationships operating across billions of years ultimately contributed to conditions on one small planet where matter learned to ask questions about itself. Seen from that perspective, the moving point of light, first noted by Galileo in 1610, occupies a surprisingly important place in the story of where we are. At this very moment, while you sit on one world, thinking about another, Io continues exactly as it always has. No pause occurs, no acknowledgement follows our attention. Deep within the moon, tidal forces continue their endless work. Rock bends, heat accumulates, reservoirs shift, pressure migrates through fractures, extending across landscapes we have never touched. The process never stops. Loki Patera remains active, its immense volcanic depression cycling through patterns that scientists can model years in advance. Prometheus continues reshaping the surrounding terrain through persistent volcanic output. Elsewhere, beneath sulfur plains and fractured crust, new eruptions may already be preparing themselves for eventual release. The machinery remains engaged. Above it all hangs Jupiter, immense and unavoidable. From Io's surface, the giant planet dominates the sky, its cloud bands stretching across a view unlike anything known on Earth. Around Jupiter extends the plasma torus, a ring of electrically charged particles supplied largely by material escaping from Io itself. The connection is continuous. Roughly 5 million amperes of electric current flow through the interaction between the moon and the giant planet. Magnetic fields guide those currents across extraordinary distances. At Jupiter's poles, auroral features brighten and fade in response. A disturbance originating at one world leaves detectable signatures on another approximately 422,000 kilometers away, which is about 262,000 miles. Everything participates. Gravity links the moons. Magnetism links the plasma. Volcanism feeds the environment surrounding the planet. Energy moves through the system with remarkable consistency, each process influencing the next through relationships established long ago. But none of it requires witnesses. The volcanic eruptions do not become more real when observed. The currents do not strengthen because instruments measure them. The resonance does not continue because scientists understand it. These events proceed according to physical laws that operated long before human beings existed. There is something steady in that realization. The universe functioned for billions of years before Earth formed. Stars were born and disappeared. Galaxies collided, planets emerged and vanished. Throughout all of it, nature required no audience, no interpretation, and no recognition. Yet something unusual happened. On one small planet, chemistry eventually became biology. Biology became awareness. Awareness became curiosity. Over immense stretches of time, that curiosity developed mathematics, telescopes, spacecraft, detectors, and theories capable of reaching far beyond immediate survival. A remarkable chain. Through that chain, we learned to measure temperatures on distant lava lakes. We mapped volcanic centers on a moon orbiting another planet. We calculated the movement of molten rock across surfaces hundreds of millions of kilometers away. We predicted behaviors hidden within environments no human being will ever naturally experience. And often, the predictions proved correct. That achievement lingers after the details fade, more than the eruptions, more than the scale, more than the immense currents crossing space. What remains is the fact that understanding reached this far at all. Across distances almost beyond intuition, a species briefly appeared and learned how to know a place like Io. That may be the most extraordinary part of the story. before forests spread across continents, before fish explored ancient seas, before any creature possessed eyes capable of looking upward. Io was already burning. The eruptions had already begun. Across spans of time that challenge imagination, tidal forces continued their work. Orbit after orbit, the moon flexed beneath Jupiter's gravity. Heat accumulated. Magma moved. The surface renewed itself again and again, while Earth was still passing through chapters long, erased from its own crust. The process endured. Given the remarkable stability of the resonance that drives it, Io will likely continue erupting far into the future. Civilizations may rise and disappear. Species may transform beyond recognition. Entire branches of life may come and go, while the volcanic engine beneath Io continues converting gravitational motion into heat. The fire was never intended for us. No purpose guided its beginning. No audience determines its continuation. Three worlds remain locked together in an orbital relationship governed by physics, and the visible result is a moon covered in lava lakes, volcanic plumes, sulfur plains, and constantly changing terrain. Yet the connection reaches farther than distance suggests. The same resonance helping sustain Io's activity contributes to the conditions that keep Europa's hidden ocean liquid. The same style of intensely hot volcanism visible on Io today resembles processes that shaped Earth's distant past. The same principle of tidal heating appears throughout planetary systems, wherever mass, distance, and orbital geometry align in the right combination. One mechanism, many outcomes. When we follow that thread, the boundaries between worlds become less distinct. The physics operating within Jupiter's system also influences our own planet. Gravity raises tides across Earth's oceans. Internal heat drives tectonic activity. Orbital relationships shape climates and environments over immense periods. We belong to the same framework. Io stands out because the underlying machinery remains exposed. There are few moderating layers. Little concealment exists. The conversion of gravitational energy into geological activity occurs with such intensity that even spacecraft crossing hundreds of millions of kilometers can detect its effects immediately. The engine reveals itself. Look toward Jupiter in the night sky, and you are seeing only part of the story. Near that bright point, unseen without powerful instruments, Io continues its orbit. Roughly every 42 hours, it completes another circuit. Volcanic centers remain active. Material escapes into surrounding space. Electrical currents flow through Jupiter's magnetic environment. Neighboring moons continue responding to the same gravitational choreography. All of it continues tonight. Whether observed or ignored, the system proceeds according to the same physical rules that governed it yesterday and will govern it tomorrow. The universe does not pause for attention, approval, or understanding, but understanding still matters. Something changes when you follow the chain from orbital resonance to internal heat, from internal heat to volcanism, from volcanism to chemistry, and from chemistry to questions about habitability and life. The chain is real. Every link is connected. Perhaps that is what remains after the details fade. A human mind on one small world became capable of tracing that chain across space and time, from a handmade telescope in 1610 to glowing lava lakes hundreds of millions of kilometers away. That ability may be the most extraordinary thing in the entire story.